Hello, my name is Rodolfo Haber. I'm a researcher from the Center for Automation and Robotics of Politécnica de Madrid and the Spanish Council for Scientific Research. I'm nowadays the director of the research center, and I'm going to present the paper entitled Digital Twin-Based Optimization on the Basis of Grey Wolf Method, a case study on motion control systems. This paper is co-authored with colleagues from the University of Technology Warsaw, the University of Belgrade, and Politecnico de Milano. This is the scope of this presentation, in which topics that we are going to address: who we are, goals and approach of this work, techniques and method, some evaluation results, and finally some concluding remarks. Okay, as I already presented, my name is Rodolfo Haber. I'm the director of the research center, and also the head of the research group called GAME, which is the group of advanced automation of machines, highly complex processes and environments. We are very interested in developing new methods for intelligent modeling, control and supervision beyond physical processes and systems, paying attention to systems and cyber-physical systems. And this work is supported on the basis of three ongoing projects. One is a NAWA Polish agency project called IPAE. The second one is H2020 project grant Power to Power. And the last one, but not the least one, is the Cognitive Inspiration and Navigation for Autonomous Driving, which is a national research project. Here you can see the logo of Power to Power, which is a very big initiative in the field of Industry 4.0 at the European level. Okay, this work is mainly focused on how we can exploit digital twins in industrial cyber-physical systems. In this slide, we are putting the attention on four aspects that are lacking nowadays digital twins in industrial cyber-physical system. The main message that we have identified in the literature is that nowadays we are lacking of clear engineering procedures. Engineering procedures for considering real-time constraints, we are lacking systematic procedures for digital-based optimization and adaptation procedures, and we are lacking a clear method to focus on feedback system. In this slide, you can see also a diagram in which we have put in an example. This example is related with this paper, with this work, and this is an example of a typical manufacturing company in which we have several matching tools. Each matching tool has a computerized numerical control with a computer that controls the machine, and this is open. We have the possibility of communicating with other devices, and we have here in blue, the original equipment manufacturer of computerized numerical control. This is a typical example in which each machine tool has an open CNC that communicates with the manufacturer of this device, and at the same time this manufacturer has a cloud in which they have a digital twins and optimization library. The procedure, the concept that we are addressing in this paper is the possibility that have nowadays that many manufacturers are exploiting of using this communication with these matching tools on the basis of key performance indicators, and to run in the cloud or in the edge device, depending on the architecture, on the basis of digital twin to perform an optimization and adaptation and learning. And by this way, on the other side, we can update tuning parameters and perform the calibration of the control system of each machine. Okay. But indeed, four open issues are being addressed by the scientific community in relation with the digital twins. The first one is related with the bottleneck of communicating physical and virtual spaces. This is not straightforward to support interaction in real time. The second one is that the physical system is not easy to mirror this physical system due to uncertainty, complexity. Another aspect is related with that we have discrete, virtual, and continuous spaces and physical spaces, and we have to deal with. And we have also the need to include more the human behavior and interaction with the physical spaces. In this slide, at the end, we are showing 3 recent papers that we have published in IEEE Transaction Industrial Informatics and IEEE Access related with digital twins, optimizations, and automatic selection procedures for optimal parameters. Okay, what is the main goal of this paper? Okay, the main goal of this paper and the work that we have reflected in this paper is the design and application of a digital twin-based optimization method. To do what? Why we need a digital twin-based optimization method? Because we are pretty interested in optimally set control and compensation parameters of motion systems. What happened that this motion system has many nonlinearities such as friction and backslash, and what we propose in this work is to use a population-based meta-heuristic method called Grey-Wolf optimizers to carry out this optimization. But why we need to perform from the practical, from the industrial viewpoint? From the industrial viewpoint, it's important to remark that the surface quality of manufactured components. In this slide, you can see many implants in different that nowadays are being produced. That the surface quality of, for instance, of hip and knee implants, depends on the smoothness and the accuracy of the real trajectory produced in the cutting process. And this real trajectory is in the cutting process is relevant the role of the motion system. Indeed, the key variable here is the maximum position error, the peak error, because this peak error is related with the deterioration of this surface quality. And this slide we are also showing you six key parameters that later we are going to enter in details. These 6 controller and compensation parameters we are going to tune to improve this the behavior of the motion system. Okay, which techniques and methods are we going? Okay, in this slide you can see the pseudocode of the Grey-Wolf optimizer algorithms. We are not going to enter in details. You can find further details in the paper about the questions, about the procedure. Indeed, the Grey-Wolf optimization algorithms belongs to the class of novel swarm-based meta-heuristics. There are several meta-heuristics methods nowadays available, many of them inspired from the social leaderships and hunting techniques, in this case specifically in relation with gray wolves. In this slide, we are remarking the cost and objective, the cost objective function, and we are remarking the main target. What is the main target? The main target of this work is to obtain these 6 parameters related with the gains of controllers and integral gain of the controllers of the internal and external loop, but also the compensation parameters of friction at backslash that produce the minimization, that minimize the maximum peak error. And this is the main target of this. How? Okay, we have in this slide 2 things. We have on this side you can see the physical system. You can see here the computerized numerical controller, which is we have plenty of communication opportunities because this is open. This is open CNC that we can communicate with the physical system. And the physical system in this case, the platform consists of a spindle screw system, basically for longitudinal movement of the carriage. This is the carriage, and this is a longitudinal movement of the carriage. In the paper, you can find also details about the physical characteristics of this physical system, so the variables and so on. And here in the slide, you can see also the digital twin, how the digital twin is composed of two different parts. One part is the controller. In this case, is a cascade proportional plus proportional integral controller. This is a cascade controller. We are not going to enter in details in the controller because the controller can be a different one depending on the CNC manufacturer. And we have also the electromechanical system with the models and the friction. And once again, in this slide, we are showing you the cost function and the parameter. Okay, what we have done? What we have done in this paper is to compare the proposed method with the fine-tuned method. What is a fine-tuned method? Fine-tuned method is one standard method that is applied in industry, and this method is the result of a combination of experimental study and frequency response diagrams. Indeed, this method is mainly focused on tuning servo performance of CNC machine tool axis. But this method has many drawbacks, such as it's very intensive in terms of computational cost, or also in time of tuning requiring for tuning. In this slide, you can see at the end also the Gray Wolf algorithm, how it was implemented in MATLAB, and the main parameters of the algorithm that we have applied. Okay, what had been the simulation result? For simulation result, what we have done is to use basically only the digital twin. And here you can see the position error. Here you can see that the position error, the system is very precise. We are talking about few microns in the accuracy, but you can see that in gray the behavior of the position error is much better in the method that we have applied in relation with fine-tuned method. It's important to remark that what we have done is to put in the input of the digital twin a reference trajectory. This reference trajectory is used as an input. And here you can see the resulting parameters from fine-tuned method and the resulting parameters of Gray-Wolf methods and the average computing time. You can see that the average computing time is, of course, better, is faster in our proposed method, but we would like to point out, to remark the improvement in the maximum peak error here, 0.41 in relation with 1.2. But what is more remarkable, more interesting, is that this improvement in the reduction of the peak error is done without a significant increase in the control effort that is shown here. And this is rather important. We are improving the behavior without increasing too much the control effort. In the experimental results, this is a real experimental results done in this experimental platform in which we have the digital twin, we have the physical system, and once again in real time we have corroborated this improvement. Here you can see the reference position. Here you can see the error of the position error of this trajectory, and you can see in gray how the dynamic response with the parameters obtained with Gray-Wolf optimizer is much better than the fine-tuned method. It also happened here that you can see what we have already mentioned, that this improvement in the dynamic response in the error, in the position error, and in the minimization of the peak error is done without increasing the control effort. Here you can see the control signal, the current signal of both methods. Okay, conclusion. In this paper, we have presented a digital twin-based optimization method supporting on Gray-Wolf optimizers for optimal testing of these parameters. The results are very remarkable in lesser maximum peak error, better accuracy with almost the same or less control. Thank you very much.